right. Hi, everybody. We're going to start back up on day 3, I believe it is. Day 2 for me, day 3 for you all. And we're going to be doing an overview on game AI as requested by Gavin. Just in case somebody missed it from the first day, I think it's basically all the same crew, but I'll go through this fast. Hey, who am I? That's me in a different shirt. So I had a past game dev career at Zynga and EA Sports, and then I said enough of that bullshit. I went off and got my PhD in Georgia Tech, where I did some collaborations with Unity and Disney Research. And these days, I'm at the University of Alberta and the Alberta Machine Intelligence Institute with a candidacy for AI chair. So I do stuff at the intersection of AI and games, which is why this talk is especially appropriate. They'll be talking about none of my research. This is very industry focused. This talk is actually an approximation of the University of Alberta's Compute 256 Game AI, which is a class that I made when I got there. So just as a heads up, there's a lot of sort of attempting to squish down 13 weeks into 2 hours. We'll see how that goes. So I said AI, and first of all, and there's going to be ideally audience interaction here again today. What do you think of when you hear AI? What's AI? Okay, so ChatGPT is AI, or other. Sure. When NPCs are acting on their own, that's AI. Okay. Any other thoughts? What's AI? Sure, when an agent does tasks. So we've got lots of definitions here. I think these are good definitions. For the purposes of this talk, this is an AI maximalist talk. What does that mean? That means that while there's a ton of debate and lots of bad actors when it comes to what AI is, a lot of people trying to sell you on startup services and tools and things like that using quote unquote generative AI, not a real term. We're focused on the practical questions. So this is going to be a talk that's focused on what does the industry actually do with AI approaches. And most of that is, in fact, 99.9% of that is not ChatGPT and things like that. So today, we're going to basically say that AI is anything that makes decisions a human would otherwise have to make in a game. Make sense? Okay. So here's the overview, practical and brief overview of AI/machine learning in games. So we're going to talk briefly about pathing. Pathing is a massive portion of what is AI in games. Then we're going to talk about decision making. We're actually not going to talk about data science, but I'm just going to gesture at it here, mostly because we don't have time. Maybe if we somehow end up with a lot of extra time, I'll be like, yeah, let's talk about data science. But data science comes up a lot as well, right? In terms of like, hey, we have this massive user base of like thousands or millions of players. How do we learn anything about how they're playing the game or what kinds of things they're doing in the game? You kind of have to use sort of pattern recognition, clustering approaches to be able to actually understand anything there. And then we'll end with content generation, though I think, Joseph's already done a lot of stuff with content generation with at least some of you, those of you who've taken his class. And we're going to start with pathing. So let's say we're in this situation. We have Pac-Man. There's Pac-Man. Gavin's not in the room, but I noticed that he has Pac-Man tattoos, so we'll go with Pac-Man as our example. And let's say that we are being controlled by some sort of AI agent, our Pac-Man is, and we want to get to a ghost. Sort of the opposite of what you typically want to do in Pac-Man, but let's just say this is the situation. How would we go about doing this? We're in this virtual world. We have a 2D plane. We know about our position. We know about the ghost position. What do we do? Straight line. Yeah, it's self-evident. This is not a trick question. We would straight line it, right? Easy peasy. Problem. What if there's a wall in the way? How can we know how to get around this wall? What do we do? Sure, we could say that there's a way through on either end of the wall, if that's helpful for you. But how would we get there? How would we know that? Sorry? Oh, it's like you looked at my slides earlier and you saw the word pathfinding. Yeah, so we're definitely gonna have to find a path, but how do we find a path? Does that make sense? Okay, so we could do small increments at a time. So I could say like, okay, well, I can move this far forward and I'm safe. I can move this far forward and I'm safe. And I can move this far forward and I'm safe. But now what do I do? Right? I can't move forward anymore. Do I go left? Do I go right? How do I know which way is the right way to go? Does it make sense? So the tough thing here is we need some way of representing our space. This is the number one, the first thing that we're going to have to solve anytime it comes to pathfinding. We have to have some way of representing the space, a spatial representation. And the most common one of those is grids. Grids are super nice. Grids are super handy because they're going to chop up your space into areas you can go and areas you can't go, right? And now if we're in the situation where we have a Pac-Man trying to get to a ghost or a red square trying to get to a blue square, right? We can think about this in terms of, oh, okay, I now know the positions I can be in, right? But this doesn't actually tell us what the path looks like. It tells us where we can and we can't be. It doesn't tell us where the path is. But let's first think about grids a little bit more. So a grid can be represented as a graph. Does everybody know what a graph is? Does anybody not know what a graph is? Feeling okay? A graph, that's a great question. A graph is a data structure which is going to have nodes and edges, sometimes called vertices for some reason. I don't know why. But I'm going to say nodes and edges. Those edges can have directions on them or they can't. So you can say you can only move along this graph following certain edges in certain directions. Otherwise, it's just a free-for-all. Make sense? So in this case, a grid can be represented as a graph, where a graph says the node is a location we can be, and the edges between those nodes are paths we can take, little bits of paths, talking about your little bits of paths idea, little bits that we can know we can safely travel along. Make sense? So this lets us know where we can be and where we can go between. But this doesn't actually get us paths yet. So let's talk about a very, very simple approach to pathing. It's called greedy search. What we want to do is we want to find a path from the start to the goal node. What we want to do is add our neighbors of the current node to some open set list. This open set list is just a way of saying, hey, we can get here. This is a place that we can be, right? Then we want to pick the next current node from the open set that is closest to our goal position. So let's say that we're at A, we want to get to I, right? Well, I have two neighboring positions from there, so I could add B and D. Don't worry about the letters. These are arbitrary. They don't mean anything. I'm just giving an identifier to each one of these nodes. Don't worry. I could get to B and D, but now we get into this sort of problem here. I don't know if you noticed, but depending on how we measure it, B and D are equivalently far from I, right? And we only have the information that I just specified we had. We don't know ahead of time that if I keep following B, I won't actually be able to get to I. Does that make sense? So this is the problem with greedy pathfinding. If we keep on going like this, bam, we can get stuck on C and then have to go all the way back to D to G to H to I, right? And that leads to sort of weird behaviors. So nobody actually uses this. It's just the simplest thing that I can start with to give you an intuition about how we would find a path. Make sense? Okay, so how can we improve things that are greedy? We have a few options. So we could improve the heuristic. That heuristic is just the distance function of sort of how far away a node is from our goal node. We could improve greedy through a number of different ways. It could think about when it fails, right? When it catches on something. And the way that we're going to try to improve it is with A star. A star works like this. Nodes are going to have two costs. We don't just have the distance to the goal. We now also have a G score, which is the cost from getting from the start to this position. Does it make sense? And then we're going to combine that and our H score, the cost of the goal, to get this F score. This is just basically a way of saying that when we're making a decision about what's our next best node to think about, we're going to be considering both of these factors. Make sense? That's all it means. Then we're going to pick which node to choose next based on both of these scores, but there's a couple other improvements from here. I'm going to put some pseudocode. I'm sorry, this is the only pseudocode that's going to be in this whole thing, but I promise I'm going to talk you through it. It's going to be fine. This is the basic A star pseudocode. We're going to start by adding our start position to the open set, saying, hey, we can get there, right? Then we're going to keep on going while the open set is not empty. That'll happen if, for example, it's not actually possible to get to the goal from our starting position, right? We're going to look at our current from our open set. This open set.pop means we're going to grab the cheapest node according to that F score. So that's both in terms of the distance we'd have to travel to get there and the distance we think we're going to have to travel from here to get to our goal. Make sense? So we're going to grab the cheapest one of those because we think it's going to be the best option in terms of getting us to the goal fastest. If our current node is our goal, guess what? We can just reconstruct our path from there because we've now found a sequence of nodes that will get us to the goal. Make sense? If not, we're going to add our current to a closed set. This closed set is a way of saying, oh, we've already considered these nodes, right? We don't need to actually think about them anymore, right? Then for each neighbor of this current node, which is each of those neighboring positions, right? Each of the edges connected to this node, we're going to check and see if it's in the closed set. If it's in the closed set, we continue. So we just swap, keep on going through the loop. If not, we're going to calculate its G-score. We're going to see if it's not in the open set. If it's not in the open set, we're going to add it to tell us, hey, we can get here now, right? If it is in the open set, but its G-score is worse, which again, the G-score is the distance that we traveled from the beginning to this position. If we basically found that like, oh, okay, I had a route for here where I went like all the way around like this, but now I just found a new pathway where I just go straight to there. I'm going to replace that cheaper pathway to replace the longer pathway. Make sense? And that's the entirety of the algorithm. It's just that easy. And this is the pathing algorithm used in 99% of games. So if you see a character moving on their own in a video game, chances are almost certain they used A star. It's not actually the best pathing algorithm. There's a lot of better pathing algorithms, but video games industry tends to just keep on using what they know, and they know A star, and it gives you optimal paths, so we're good to go. So with that, we can solve this problem, right? So now that we know this, we would have to slice up the world into grids. And then we could say, okay, from here, I know I can get to here, to here, to here. And then between these two options, I could say, well, I can consider this one, but eventually this isn't going to get me to the goal. So I would jump back over to here, then take these other sort of pathway all the way to get to our intended position. Once I get to our intended position, I reverse my pathway to figure out how I got there from the start. And then I tell Pac-Man, follow that. Because notably, when we're pathing, we don't actually literally move the agent. The agent is like imagining in their mind, not an actual mind, imagining sort of what the path would be like to get them there. So they don't have to move at all to consider this sort of path, to come up with the path, which they can then follow to the goal. Make sense? Cool. Okay, so the most common spatial representations in games are grids or nav meshes. Grid here represented by Animal Crossing. Nintendo loves grids. They use grids a lot in their games. And there's lots of games where they obviously are using grids. Like if you played, I don't know, like Into the Breach or various other sort of games similar to that, right? There's obviously a grid present. A lot of JRPGs use grids, etc. If you have real-time movement, you're actually using a nav mesh. A nav mesh is a bit like a grid, but what if the grid was made of arbitrary cells as opposed to cells of a fixed size and shape? Make sense? Both of these can be generated, but we're not going to get into that today. But both of them, well, the nav mesh usually requires a human to then go in and edit the automatically generated nav mesh because it often has particular things that you want to add. But that's how generally all spatial representations in games work, which is pretty nice. Okay, with that, we've done it. We've talked pathing. So let's talk decision-making, data science, content creation. We're going to talk about decision-making next. So decision-making. Standard AI, which is to mean like if you were going to go try to make some sort of AI application in industry or something like that, what you would care about is making the optimal choice of action that maximizes the chance of achieving a goal, right? If you're trying to detect how much, I don't know, steel has gone into a big steel tumbler or whatever, right? You would want optimal actions, right? In games, we don't. We want the right state, the right actions to support the player's experience. Something that people who are just starting working with game AI, making NPC behaviors, is they assume that what you want is for the hardest possible enemy. No. It's trivial to make an enemy so hard in the game that no player can beat it. Guess what? That's not fun. People like enemies that are beatable, right? And so that makes this a very different kind of thing we're optimizing for. Make sense? Okay, this is now a question for the class, question for the workshop. What do we think is the simplest way to define an AI behavior in a game? Okay, I think we can get simpler than that, but state machines is an answer. Yeah, Jose? So you said finite state machines as well? I think we can get simpler than finite state machines. What do you mean by a looping behavior? Sure, but then you're not making a decision, right? We're thinking about what's the simplest way to make a decision in a game. So you could roll a dice, but that would give you a condition. Oh, hold on, we're so close. If we have a condition, what does that suggest we have? an if statement, which we can also call a rule, right? The simplest way that we can represent a behavior, an enemy behavior in a game, is a rule. So we have two parts. We have a condition, which is a logical expression that must resolve true for the rule to fire. And we have effect, what happens when the rule fires, right? This is the simplest way to do enemy AI. You say, if the player's in range, shoot at the player. If you see the player, chase the player, etc. Right? There's problems there, but it's pretty, whoop, didn't mean that. It's pretty extendable. So this actually dates back as an approach to 1968 with Block's World. In this, we had really simple sets of rules, right? We have pickup block, which allows you to pick up a block if there's nothing above it. Move block, which moves a block to a position as long as it's not blocked. Drop block, which drops a block to a position as long as it's not being blocked to be able to fall to that position, right? And this was used for sort of robotics, sort of simulated decision making with like planning and things like that. You can imagine transforming this into things for a game by thinking about this in terms of a whole bunch of rules being written, and then facts about what's happening in the game matching to the ifs using some sort of pattern matching approach, right? So it could just be a big long list of if-else statements. What a terrible idea, but you could do it that way, right? When a rule becomes activated, you can choose a current activated rule to fire, and then net some change to the facts of the world, and then you repeat. So for example, not in a blocks world now, but we could have something like this, where we have all these facts, like the health of different characters, what weapons or items they're holding, what ammo they have available to them. We could have rules about like, oh, upon certain things happening, right, you can transfer over certain behaviors to certain things, et cetera, et cetera, et cetera. This kind of approach tends to be really general, as long as the if statements, the conditions, are general enough, right? So like it doesn't matter, for example, what the situation is. If Whisker's health is less than 15 and Whisker's holding the radio, then Whisker radio calls for help, right? It doesn't matter how Whisker got put in that position, which is really general. It doesn't matter if like you as the player somehow dropped Whisker into the lava or, attacked Whisker with a grenade or with a knife. Like it doesn't matter. If the conditions are general enough, it's going to be really, really general and nice. This kind of rules-based decision-making is really only used by one company. It's Arcane Studios. These are the people who made Dishonored 2 and Deathloop and things like that. And they really like it because these are sort of semi-games, like games where you have a lot of flexibility in terms of the ways you go about solving problems, right? Weird abilities, weird items, things like that. And this means that the enemy AI can respond appropriately regardless of what you're doing. Make sense? Nobody else does this but them because it's sort of finicky, right? It takes a lot of effort to design a good set of rules. Okay, here's the big problem. Most actions require more than one rule, right? So for example, if you're shooting, well, shooting requires not just the shoot action. You also have to figure out if you have enough ammo. You also have to maybe reload if you don't have enough ammo. You have to make sure you have a shot before you shoot, etc. Patrolling, similarly, farming, sleeping, hiding, hunting, etc., etc., etc. Any action you would think about an enemy or a just non-player character doing in a game probably has some serious effort in terms of like the amount of rules you'd have to author to represent it. So here, my finite state fans, is where we'll talk about states, right? So instead of thinking about this as just as if statements, we can think about getting a whole bunch of code together, a whole bunch of behavior together, and bundling that into what we'll call a state. Right? So each of these could be a state. So most agents have more than one state. So for example, we might have a guard that can move from patrolling, attacking to hunting. We might have a farmer that can move from farming, patrolling to sleeping, right? For example. One of the nice things here is we can reuse states, right? Which gives us some really nice code reuse, which is always a plus. So finite state machines. Clearly, some of you at least already know what a finite state machine is, but let's go through it anyway. So historically, this is a mathematical model of computation, but we don't care about that. This is basically an approach where we're going to determine what one state, or action in this case, are we going to fire on a particular game frame, right? And I already told you yesterday about what game frames are, right? This is a general game AI model for agent behavior with some finite number of states, S, an initial state I, a transition function, t of s to s prime, that tells us when do we move between states, and then 0 or more final states. So for example, Here's like a little FSM example. So this would be for like a little treasure hunting NPC character, right? We have 3 states: gather treasure, flee, and fight. If we're gathering treasure, we can, if we spot a monster, we would have to move to flee. So these arrows that you're seeing here are telling us things that we have to do, right? If we're fleeing and we don't see a monster anymore, then we go back to gathering treasure. If we're fleeing and we're cornered, only then would we fight the monster. They're sort of cowardly, right? And then if the monster is dead, we go back to gathering treasure, right? So this is the way this sort of works. And there's a couple interesting things with just this finite state machine, right? Because there's no way for this character to die. Because maybe this character is like a core character to your story or something like that. You don't actually want them to die, but you want them to behave in some way that fits their personality and sort of sells them as really living in the world. Make sense? Okay. In terms of implementations, you have a lot of options when it comes to FSMs. You could throw it all in a switch statement. This is really simple, but it's not at all extendable, right? If you had just like a big set of if and else's, you could technically do a finite state machine like that, but what a terrible idea. You can't do any code reuse or anything like that. So that would look something like this, right? Throw in some ID for the state, and then make decisions based on that ID. You can do the state as a class. This is much more recommended. In the state as a class, an agent carries a reference to their current state. This is super extendable, and it means that you can have different enemies or different NPCs using the same states, right? Because they can instantiate their own version of the same state, which is really handy. Then you can also do a state as a table. This is really cool because this can be stored separately. So we could actually have literally like a Microsoft Excel document, which has, here's the states that exist, here's the rules at which they should move between them, and the game can load them up to control the agent's behaviors. Game designers who don't program really like this kind of setup because it means that they can tweak things really easily, right? Without having to do any code. And in the table, it would look something like this, right? So that's that exact same sort of graph-based representation, but now I've done it as a table. Make sense? Cool. Okay, let's talk about Pac-Man some more. So Pac-Man is really interesting in terms of FSMs. Can anybody tell me why? Yeah. Each of the ghosts has different behaviors. It's true. Did anybody ever play Pac-Man? Show of hands. I know Gavin has like a whole Pac-Man themed like existence. I was really hoping he'd be in the room here so I could like make references, but unfortunately, it's not so worth working. But anybody ever see this page here? It's like the first thing you load up when you're like on the old arcade version. And you'll note they all have nicknames. So we have, we have nicknames, and then we have the character, the sort of personality. So we have Blinky, the Shadow, Pinky, Speedy, Inky is Bashful, and Clyde is Pokey. And this is actually meant to be a description of the behaviors that each one of them had that were unique. But while each of them have these sort of unique behaviors, it's also true that each of them have some shared behaviors, right? Because anybody who's played Pac-Man knows if you get a power pellet, they go to this sort of like scared state where you can eat them, right? So the actual way that the finite state machine works in Pac-Man is something like this. We would have unique states for Blinky, Pinky, Inky, and Clyde. But then we have shared states for scatter, which I can get into, but scatter is just this thing where every X amount of seconds they have to go into the corners. It's basically to give you like a little bit of a rhythm and like a breather. And then they have a scared state. And there's actually also like an eyes state separately and like a respawning state, but I just didn't put them on the slides. We can imagine them. And then basically you'd have different, arrows connecting for different entities, right? And this sort of graph for each one of these different things, each one of these different sets of arrows would define a particular enemy's sort of character or personality, their behavior sets. Does that make sense? Okay, let's look at an example, which is the next slide. We're making pretty good time. I think we'll be all right. Kamloops FSM example. Here we go. And as I did yesterday, I will put these in a zip file and I'll send them to people, and you can get these later if you want them. Cool? Come on. Unity, of course, is going to take a while. I'm also opening up this in Unity 2018, so it's going to look a little bit different than the version we did yesterday. It's in light mode. Ew, gross, light mode. So let's first take a look at what this looks like. So this is a tiny little Pac-Man clone. So I can click around, and that will control Pac-Man. And there we can see we have Blinky. Here comes Blinky. He's going to kill me, and I'm dead, right? There's no lives or anything. It's just I would infinitely respawn. If I just sit here for a while, Blinky will keep on getting me. One of the other nice things about this setup that I'm giving you is We could also, for example, grab like oh no, I don't want random agent. I want greedy agent. We would replace our Pac-Man really easy. So here's a greedy Pac-Man. We'll just go to the closest pellet, right? And just keep on going like that. And so we can sort of watch, hey ma, no hands, as we watch as our Pac-Man is slowly killed by Blinky. So you can see several states in there, right? I don't know if you just noticed, but we had the regular Blinky state where he was red, and then we had a distinct Blinky state where they were sort of the dark blue. We'll watch it again because this is going to be deterministic. There we go. Right? And as soon as Pac-Man gets, oh, I didn't get him that time. There is a little bit of randomness with when they're in the sort of blue state. Oh, there we go. You see the eyes come up, and then they sort of respawn once they reach the middle. So let's take a look at what that implementation actually functionally looks like. So we have, oh, this is going to take a hot second because it's going to open up Visual Studio. My bad. We have this setup where, yeah, it's actually not so bad. We have this setup where this right here, the thing I'm loading right here, Blinky, this is the entirety of how we initialize our agent. All we do, this is literally all the code to start us off. And all it's doing is it's saying, okay, to initialize, we are going to set our current state to the chase state, which is the distinct Blinky behavior state. And then we're going to enter that state. And then all of the other logic is held in the states. We do nothing else for the setup. So it's really simple, right? We just tell it where to start, and then we just sort of let it go based on the states, right? Let's actually take a look at what that chase state looks like. For reference, this is also really simple. We can see here. This just handles following the Pac-Man, so we're going to grab Pac-Man's location. This figures out if we're close enough to Pac-Man and kills the Pac-Man if so. This tells us the transition function for when we would transition to the scatter state, which is another one of these states, right? And this will take an argument, which is the corner that this ghost should target, right? Then we have a if Pac-Man just ate a power pellet, enter the frightened state, and otherwise we just keep targeting Pac-Man. And notably, we return the current state if we stay in it. So this is really handy, right? It tells us every single frame we're either going to be returning a new state because we transitioned to it, or we return the same one because we stayed in it. Make sense? So this is really, really simple. So as an example here, it's an example of how simple this is. Let me show you how we would go about making a new ghost. So I've already set this up with Pinky, but Pinky right now is just an exact duplicate of Clyde. So this Pinky state is This Pinky state is exactly the same thing as the chase state. Now, it's good because we actually want a lot of the same transitions, but it's slightly different in terms of what we would want to have the unique behaviors of this agent, right? If you actually take a look at like Pac-Man's code, the only difference between Pinky and Blinky, the red one and the pink one, is that the red one directly targets Pac-Man's position, but the pink one targets 2 grid cells in front of Pac-Man's position, right? So guess what? That's a super easy thing to do. Rather than setting the target to this, we would grab the facing position of Pac-Man and just say we're going to target a little bit ahead, right? We would also want to target not the exact same position for our scatter state, but I think actually the other corner, right? And that's it. Now we have a new character with completely new behaviors, right? Isn't that nice? All because most of the logic is shared. So most of the logic just lives in these other classes. And as you'll see here in a second, there's Pinky. Ignore the fact that they started as Pinky. That's just for ease of instantiating, right? But there's Pinky, and Pinky's going to target the positions just a little bit befront of Pac-Man. Cool? So that's it. It's just that simple. Any questions on that? Obviously, I picked Pac-Man here because Pac-Man is a very simple finite state machine. There's like 4 states for each of these ghosts, but like 3 of those states are reused across them. So it's a great example of how much bang for you buck you can get with a finite state machine. Anyway, let's keep trucking. So finite state machines get used a lot in modern games. So like The Last of Us Part 2 used finite state machines. Cyberpunk 2077 used finite state machines. Nintendo loves finite state machines. They basically use finite state machines in every single game that they have. But that said, there is one approach which is more popular than finite state machines. Does anybody know it off the top of their head? Yeah. Oh, you're close. But let's talk about the problems with rules and FSMs first. So rules, they're great for emergent behavior, but they're bad for control, right? So if you have a particular thing you want an AI agent to do at a particular moment, you would have to define a whole bunch of really specific rules for that, which would take a lot of effort, right? Rules, on the other hand, are great for designer control. I showed you just a second ago how you could literally just have like an Excel sheet and let your designers go crazy with that, right? But they're really brittle. So it's really easy to get stuck in a particular state. If you've ever been playing a video game and you've noted that a character like gets stuck taking the same action over and over again, like walking into a wall or continually shooting or something like that, chances are really high they got stuck in a state they have no transition out of. Make sense? So that's the problem with those. We can fix both of those problems with something called behavior trees, also called B trees. So close to decision trees, but actually quite a bit different in terms of implementation. So behavior trees look like this. I just grabbed, this is Unreal Engine's implementation of behavior trees. They just have a built-in one. It looks like this. But then rather than a general graph, which is what finite state machines use, right? It's just a directed graph. It can even be cyclic, right? They don't care. Behavior trees use a tree. Does anybody know what a tree, or sorry, does anybody not know what a tree is if I say a tree in terms of graph theory? Okay, that's fine. So a tree is just a graph that has a direction, right? So all of the nodes go from some root node and they come out of that, and things can only flow from the root. Does that make sense? Now it's a little bit a bit of a misnomer because what it looks like is a root system, right? This is a tree. But imagine if you flipped it 180 degrees, so now it's standing up. Now you can see how it looks like a tree, right? And computer scientists are upside down and backwards, and so we call them trees. I don't know. Anyway, so at every iteration of the behavior tree, we're going to start the root. This is really interesting. We can think about the root as kind of like a default state, as like the default thing, except there's no behavior in the root. The root is just telling us, here's where we start every single time, and then we're going to walk the tree downwards until we find a leaf node that we're actually going to execute. We're actually going to do something about. So we're going to walk to one leaf node, which is just some childless node, which is equivalent to our states. Everything else in the behavior tree are things about making decisions about what states you go to and when. Does it make sense? So every other node but the root and the leaf nodes is about figuring out what leaf node do we go to under what conditions. So there's lots of nodes that aren't states that help structure our behaviors. And notably, one node fires per tick. It's similar to finite state machines. We'll have one state that fires per tick. In this case, one node fires for every single tick, every single frame of the game. So each node is going to keep track of our current child to execute, and at the start of a tick or a frame, walk the tree to find our current node. And if it's the same as the previous one, we just keep going from the previous one, right? We can retain the information, keep that instantiation going. Nodes can return one of true, false, or none. And behavior trees are used everywhere. Basically, every single big budget AAA game uses behavior trees. Basically, since Halo 2. Halo 2 was a revelation in terms of enemy AI because they used behavior trees, which meant it didn't have these sorts of problems that other previous AI systems had around being brittle, around being stuck in a certain thing, about not being general enough, etc. So there's lots of node types in behavior trees. I'm not going to do this exhaustively, and names differ depending on the implementation. I just want to give you a sort of overview to get some intuitions about these things. So there's actions. These are do something in the world. These are the leaves of the tree, the childless nodes. There's selectors, which make a decision based on some world condition. So this is kind of like an if, right? This is kind of like a rule. But notably, it's making a decision potentially between branches of a tree, not in terms of what do you do immediately, but just which branch of a tree do you go down, right? Prioritized lists does a success if any child succeeds in order. So you're basically going to keep on trying things, and if any of them succeeded, the whole thing succeeded. So for example, you could have a prioritized list which was like, okay, this prioritized list is about finding food. And the first thing that I could do is I could check to see, do I have any food in the pantry? If that succeeded, the whole thing succeeded. I don't need to go further down the prioritized list. But if that didn't succeed, I might need to go to the grocery store. If the grocery store is out of the kind of food I like, maybe I have to go to a restaurant, right? But if any of these succeed along the way, the whole thing succeeded. Does that make sense? Cool. Sequences are the opposite. There's a failure if any child fails in order. So sequences are really handy in cases where you have to think about behaviors that depend on each other. So for example, we could say, like, I wanted to cook something at a campfire. Well, if I have to do that, first I need to gather wood. If it fails, the whole thing is over, right? I can't start a fire. If I've got wood, but I don't have anything to start the fire with, guess what? It's also fail. But if I have wood and I have something to start the fire with, then I need something to actually cook on the fire. If I don't have that, again, everything's failed. Does this make sense? So this is really good for behaviors which sort of have the sense as if they're like planning things out ahead of time, as if you have to actually think through the steps of things. Of course, it's not. It's all defined by a human, right? But it looks that way. You have probabilistic, which is going to choose probabilistic from set, or one-off, which can be random or prioritized, which is picking a random single child from some list or with a priority. Make sense? There's some implementation stuff here. This doesn't super matter, but I wanted to show you how simple it can be to implement these things. So for example, our action might just have a run. If the execution conditions for actually trying to do this action are not met, sorry, return false. Otherwise, whatever you do, what you need to do, and you would return true if you succeeded at doing it, false if you failed at doing it, and none if you just aren't quite done yet. Because again, this is firing every tick, every frame. We're not going to possibly finish every activity in 1/60th of a second, right? You can then have a priority list, which is very similar. It also has a run thing. It also can return true, false, or none, but it depends on whether any of its children has succeeded, whether it returns one of those, just in the way that I just explained. Same thing for a sequence, and so on and so forth. So here's an example of actually putting it all together. So this would be for sort of like a prey animal in a game, like imagine something like that. So we start at the root every single time. We then enter a prioritized list, and the first thing we would try to do is flee. Now, isn't that interesting, right? The first thing we start with is flee. This actually tells us a lot about the sort of character of this non-player character, that the default thing they do is they try to flee. Now, if that fails, no worries. We would just keep on going to the prioritized list, right? So in the very next frame, we would go root, prioritized list. We don't need to try to flee anymore. So then we could try to find food. If find food succeeds, guess what? The whole thing succeeded. And then we would go back up to the beginning of the prioritized list again. If that fails, we can't find any food, we just go to idle and just keep on going like that. Make sense? And there's several of these where we could select down into a different thing, but we basically follow that every single frame of the game, and that tells us what we should do. The nice thing about this, right, is if I'm over here in eat, like if I'm currently eating the food and then like somebody takes away my food, I'm not stuck in this state of like continually doing the eat animation even though my food's gone, right? Instead, I'm always starting back up at the root every single frame. And that means that we can avoid this sort of very classic older AI FSM problem of getting stuck in a particular state. Make sense? Cool. Okay, so some advantages. This gives us the appearance of goal-driven behavior. It isn't really goal-driven, but it looks goal-driven. And it leads to multi-step behavior, which is really cool, right? So you can get a sense of like, this character actually has like a plan. They're actually doing things in order. It is slower on average than FSM's, finite state machines, because finite state machines only have to consider what states can we go to from here. This has to walk down to a new node every single time. And they can recover nicely from errors. There's some disadvantage. It's not actually thinking ahead about unique situations, so it can't actually plan. And it's only as good as the designer makes it. It's just basically following recipes, but that's the same thing for finite state machines and rules. Finally, it can be more confusing and unintuitive for non-programmers, right? So we can't do the same thing we could with a finite state machine. We can't literally just give somebody a table and have them fill it in to tell us how a character should behave. Cool? Okay. Quick important note, I think this is an important thing to put across, even just a simple thing like this. Any desired set of behaviors that can be represented as a B tree can be represented as an FSM and vice versa. It's really just how much effort you're putting into it and what kinds of behaviors you want to represent. The difference is that sequence of actions would take more work in an FSM. We'd have to do some extra variable tracking outside of the FSM to be able to handle sequences. And error recovery, FSMs would require way more state transitions, way more of those edges or linkages to be able to do what B trees do naturally. Make sense? Cool. Okay, with that, this is an estimate. I want percentages here, so give me a value between 1 and 100. How many modern games do you think that use systems like one of these three that I've just showed in front of you? Most of them. Okay, that's not a number. I mean, anything that has decision making in it. If it has decision making, what percentage do you think uses an approach like one of these three? 99? Any other guesses? 100? Okay. Anyone wants to guess a lower number? 72, 40? Okay, so some lower guesses. So probably, if I were to guess, since Halo 2, every single game has used an approach like this that has released recently in terms of a AAA or quad studio. About 95% or more of published games use one of these three: production rule systems, finite state machines, or behavior trees. That said, there are more decision-making options out there. So for example, you could combine FSMs and B trees. And if you do that, B-tress, for some reason wrote it like that. For example, in Final Fantasy 15, which is the one, well, I don't know why that's so low resolution. It wasn't low resolution on my screen. But anyway, this is the one where then the car, they're doing the car ride for the whole game. This one actually uses a weird combo of FSMs and behavior trees. And there's other stuff as well. I've linked down there the Game AI Pro things, which goes over some other cool, weirder things on the side. The only sort of 5%, the biggest portion of that remaining 5%, uses this approach called planning, and specifically an approach called hierarchical task networks. But that's used on like literally enough games in the recent years that I could count on one hand the number of like published AAA games that are using it. So it's super, super less common compared to one of these other three. Make sense? Cool. Okay, so with that, you've got a whole bunch of that stuff covered. But one thing we didn't really talk about is like dialogue and replayability in games, right? So like we didn't talk about how you make decisions around dialogue basically at all, right? So, did people play Hades? Who played Hades? Show of hands. Oh my gosh, only two of you? Such a good game. What are you doing? Hades 2 is coming out. Okay, well, if there's only two of you, we're going to watch a little bit of the People Make Games video on Hades, just the beginning of it, so I can give you a sense of sort of how does this work? How does their sort of dialogue in the game look like?
Hades, just like everything that Supergiant Games makes, is filled to the brim with observations about you, the player. There's one I really like in the first boss fight with Meg, for example, that begins with this line. She's basically telling Zack here that he wouldn't stand a chance against her without all of those upgrades that you've suddenly been unlocking for him as you play. It's a pretty simple plot, to be honest. However, if you then, on your next run, with all of those upgrades, which almost nobody will ever do, by the way, she references that in the next fight. Since something different about you, Zacharias. You will take this. You said you weren't trying to compete with me.
So, that gives you a sense of what's going on in Hades, right? In fact, that's just one example of what is very rich in terms of the dialogue system in the game. It's constantly trying to say really specific things about what your specific player experience has been like. Anyway, so what do we think the simplest dialogue system in games would be? This is not a trick question. The same one! If this, say that, right? It's a rule. It's exactly the same thing, right? This is not meant to be anything like nefarious on my end. The simplest way to do this, we could like do something where we could take their environment, whatever the environment is in your games, it doesn't really matter what it is. The environment could be like, the decisions the player just made in a visual novel. It could be, what's on screen at the moment, etc. And we could turn all of those things in environments into facts. And then we could basically write a line of dialogue for every single fact, right? That's all we would take. Now let's take a look at a classic Valve example. This was an in-house demo, which they released publicly at a GDC talk. So I'm not like being evil by having this video clip and showing it to you all. I have other video clips on my computer I can't show you, but this one's I certainly can, on sort of what that looks like if you just do this really simple thing.
I know it's tall. That's an old guy. I don't want to alarm anyone, but I see a sucky cat. Look out, mates. The world's sick.
Computer appears to be broken.
Anyone want to see me break this cinder block with me ass? Anyone? Oh, shoot. Supposed to fucking miss this. Danger. Flammable materials. Look at me, that does sound dangerous. Look, Chinese fruits.
So It's a little bit like a small child exposed in an environment, right? Like there's no connection between any of the things happening. You're just sort of saying stuff all the time, right? So what's going on here is for each character, once per every 10 seconds, they're going to find objects in their vision cones. There's like a cone being projected outward. Think about like the perspective camera that we just looked at the other day. And anything that's in there, it's going to look and see, hey, do I have an object? Do I have a dialogue line for this object? And if so, I'm going to say it, right? Which isn't great. So this is again a question for you all. How could we extend this framework to allow for agents to have a conversation? Yeah, sure. Ah, so we could certainly do that, right? And if we're doing like an interactive narrative, it'd be very normal to use something called like sometimes a story graph or a plot graph or things like this, which allow us to exactly control these things. But let's say in this case that we want to have things that are a little bit more not controlled in that way. So we're not seeing exactly when these things should be happening. But it's a great answer that gets used all the time in all kinds of different games. Any other thoughts? How could we do it? No ideas? Well, let's think about this for a second. I introduced these things to you all in a very specific ordering, right? When we were just talking about rules earlier, we just had like rules by themselves. Were rules limited to only having effects around dialogue lines? No, right? You can have a rule having any effect you wanted. So you could, for example, have a rule effect which also says, okay, say this dialogue line, but also say to every other character, hey, here's a variable that says I just said that dialogue line. And now if you have an if statement, if you have a condition inside your set of dialogue that says if that dialogue, that first line was just said, say this second one, now we can have a conversation going back and forth. Does it make sense? So what we can do is we can add an extra effect to every production rule that writes a new fact into the world. So for example, if I see a barrel, I could say the barrel line and write a Boolean like seen barrel into the world. Then, if I have somebody else see the barrel and that seen barrel has been set, this Boolean has been set in the world, they can say a new line related to that. So let's take a look at what that looks like.
Danger. When perhaps.
Caution. Alert.
Once.
Precautional. Just like my life since. Dear, seven is not
No. It's true. I haven't played. I am trying to use something.
Oh, out.
Well, it is a prison base.
Yes, probably in it. Oh, that's a rather shabby crate.
Oh my god, it's horrible.
Ah, let's never looked at it again.
Stop looking at it.
So you've got something here, right? They actually feel more like characters. Does anybody play like Apex Legends or Overwatch 2 or Valorant or any games like this? Okay, so some of you. If you ever notice that the characters will like have little interactions, little back and forths like this is literally how they do it. They're just saying like, hey, is anything happening right now? Have we said anything for a little bit? Or is it the beginning of the match and nothing's really happening yet? Let's randomly target one of these, say one of these, and then if there's another character there, they can respond and you can go back and forth like this, right? But Hades does this other thing that goes beyond just sort of having, this back and forth, which is that it can reference things in a long-term way, right? So this is, a little bit low on the screen, so people further back may not be able to read it. And I don't know if it's readable on the stream, so I'm going to read it out loud. This is Artemis, and she says, let's see, you blundered headlong into nature for the past 6 chambers or more, and you made such a racket I could almost hear it from Olympus. I have to say, your hunting skills are rather unconventional. So how could we figure out that? How could we figure out when it's appropriate to say a line like this, that it's been 6 chambers or more since you last ran into Artemis?
Very helpful.
Exactly, right? Who says we're limited to Booleans? We can store whatever kind of variables we want. We're CS people. We are unto gods. So what we can do here is we can take a long-term memory. This is not something that games like Valorant or Apex Legends or whatever do, but they could if they weren't, cowards. They could change from writing just a Boolean into the world to an integer, for example. So we could see a barrel, we could say the barrel line and write seen barrel plus equals to 1 to the world. So we're going to increment whatever that was at. And then if we have a particular line about a particular value of that, then we can say it. Make sense? Cool. Let's one more example of, hey, what on earth happens if you do this?
This is the time of night I'm afraid might contain a bacteria. This is a huge minefield, possibly from things. Oh, a leprechaun!
It's a dog. It's just a dog.
Bloody hell. You won't fool me again, leprechaun. Oh,
Yeah.
leprechaun machine.
Brings private reserve of urine.
So in this way, you can have these sort of long form jokes, right, that you're taking a long time to build up to, that you have several riffs on, et cetera, et cetera. It allows for sort of the sort of long-term, storytelling that you would otherwise have to do by really quickly hard coding these things. But in this way, it can be really natural and just sort of occurring whenever it's appropriate. Make sense? Okay, cool. So if you wanted variety, what you could basically think about is then taking this approach and basically having to author a different line for the same conditions, which you could then select based on sort of what's the most thing, the line that we've said the least that's the most appropriate to the situation, the sort of most constrained to it. And that's sort of how the sort of Hades systems work. Make sense? Cool. So Hades has this other big thing happening with it, which is that the levels are procedural, right? And I know Joseph already has a class. I don't know how many people were in Joseph's PCG class? Okay, just one person. Okay, phew. Oh, two people. Okay. Okay. Okay, so this is an advertisement. This section of the talk is an advertisement for that course. So let's talk about this last one of these things, which is PCG, procedural content generation. So if we're talking about replayability, we're generally talking about having some sort of PCG system in your game. If I say PCG, do people know what I mean? Show of hands, do you know what I mean? Okay, most of you. So PCG, to break it down, we have procedural, which means we're following an algorithm of some sort. We have content, which is some kind of content. That's not surprising. And we have generation, which is generation. That's sort of self-evident, right? So in terms of the content that we can make, we can do all kinds of different things. So we can do game bits, which are like pieces of a game. So like the Borderlands series, all the guns are procedural. Speed tree, which is, generating trees, but can also be used for like buildings. If you saw any recent Marvel movie that had CG in it and there were CG trees in it, they're actually using speed tree for that these days. So it's get used in film and games and stuff like that. And No Man's Sky. No Man's Sky is perhaps the biggest example of like just doing everything with PCG, and all the animals and all the people and all the land masses and stuff are all PCG. Another kind of content we can do is game space. So we can go all the way back to Rogue. Did anybody play? Has anybody played Rogue in the game? In this room? No. Okay. So Rogue is unsurprisingly where we get the word rogue-like from, right? This is a very sort of most popular early example of PCG. You can see with ASCII graphics still at this point. It's not actually the first game with PCG. That's Escape from Apple Manor, which was a year earlier, but that's pedantic. Things like Remnant from the Ashes or Spelunky, or this little game, you probably haven't heard of it. It's called Minecraft. People familiar with this one? Yeah, maybe a little bit. I laugh, or I joke with this one because, for some reason, despite coming out now, 15 years ago, 20 years ago? I don't know exactly. But like, it's still for some reason wildly popular. And of course, with Minecraft, right, the entire world is procedurally generated, right? So we can also generate game scenarios. This is not as common. But you can generate scenarios in games, by which I mean like stories or quests. So for example, Skyrim has Radiant quests. The same thing was true in like Fallout 4, for example. They also had Radiant quests, these generated quests. Dwarf Fortress has generated whole histories, whole stories of cultures. Same thing with Caves of Cud and Elsinore, which are sort of more indie side of things. The big thing that I want you to know from this part of the talk is that PCG isn't magic. Basically, what's happening with PCG is I want you to imagine trying to write down instructions so someone you will never meet is going to create a level or puzzle or creature for your video game, right? It's tough, but it's doable. And of course, the other problem here is that the person you're writing these instructions for is a computer. So you can't reference like particular media touchstones or things like that, right? You have to be really, really specific with it. And PCG can also sync things. So there's this little game called Mass Effect Andromeda. Has anybody heard of Mass Effect Andromeda? Did anybody play Mass Effect Andromeda? That's what I thought. So Mass Effect Andromeda had a troubled development cycle. It was in development for 5 years, but most of the development took part in the last 1.5 years of those 5 years. The culprit, in part, was PCG. They were trying to do No Man's Sky before No Man's Sky. They were going to set it up so that the whole galaxy that you were going to was procedurally generated to be unique to your player. But then they also were going to have this like hand-authored story and companion system and stuff like that. And unsurprisingly, those did not go together. They mixed like oil and water. And the game spent 3.5 years just sort of like churning with these ideas before they gave up on them. Yeah, well, you weren't there, so what are you going to do? They certainly had other people. Apparently, Gavin bought the deluxe edition of Mass Effect Andromeda. Sorry, Gavin. Okay, and then there's also Spelunky. Did anybody play Spelunky? Oh, so sad. The children, they have no culture. So Spelunky is perhaps the reason why PCG. It's actually made Spelunky might be the reason why Mass Effect Andromeda tried to do PCG and failed. Spelunky was this indie game that was wildly popular at the time. Basically, had one creator, this guy named Derek Yu, and it used PCG to basically have, generated levels that were distinct every time. We would now probably call it like a roguelite or a like or something like that. We didn't necessarily talk about that in these terms at the time. But from having basically this massive game created by basically a single person, people had this false sense of, oh, with PCG, you can do the work of 100 people with one person. Why not use it in every single video game? Turns out it's not a good idea. But PCG was, in this case, he did PCG with constructed grammar of hand-authored chunks. So he basically authored chunks of levels and then rules about how they could fit together. And that's how the levels were created. And it led to this really nice sort of like handcrafted feeling levels with a lot of variety and a larger game that a single developer could normally create. But it took a lot of work on his part to be able to accomplish it and a lot of like clever things. If you want, there's a whole book about it. It's not a rude thing to have an eggplant on the title, the cover. It's just an item in the game. But it's a really good book by Derek Yu about how he created it. There's also a really good Game Maker's Toolkit video actually on it. If you like Game Maker's Toolkit, recommended watching this Splunky video. Okay, so there's 3 major method categories when it comes to PCG. The first of these is we'll call constructive methods. People have different names for these. I don't know what terms Joseph likes, for example, but I tend to call these constructive methods. These are methods that build up content piece by piece according to particular rules, where the pieces are either hand-authored or generated themselves. Then we have search-based methods. In search-based methods, we define a search space where every point is a usable piece of content. So every point in the space is a piece of content. Then we're going to optimize this space according to some hand-authored heuristics and operators. And then we have machine learning-based methods where we train on existing data and try to produce novel data based on sampling from that learned latent space. We're actually not going to talk about either of the other two. I ended up changing things out a little bit later on. Let's talk about constructive PCG. So you can think about constructive PCG as basically like building up like Lego or Diplo blocks, right? So we have these pre-existing blocks, and what the algorithm is doing is it's figuring out how is it going to rearrange them to make something new. Cool? So we're building up content piece by piece. You have slots that get filled by tokens and constrained by rules. So you can think about the slots as being like those little holes at the bottom of the Lego or the Diplo thing that like tells you how you can slot things in. And the rules would be like, oh, well, this piece has to go with this piece, right? So this is by far, it's not even close, the most popular PCG method with actual game devs. Not for academics, we're weirdos, we do weird stuff. But actual game devs use these. So if we're talking about constructive PCG for game spaces, for example, you can think about cellular automata. This is an old classic. Nobody really uses it, but I like to bring it up anyway. Templates, which is the most common thing, and then noise, second most common thing. So cellular automata, this is actually originally from the 1940s, if you can believe it. So Ulam and Newman, if you've heard about like Conway's Game of Life, for example, that's an example of a cellular automata. There's an example from Terrain. You can click on that on your own if you want to go back and take a look later. But basically, it's going to sort of make a whole bunch of local decisions in terms of, actually, we're going to click on it. Oh no, I think this video died, so we can't click on it. I'm so sorry. I just found that out recently. I should have taken it out. But anyway, local positions are going to percolate through the content until some hand-authored stopping point. So this was used a lot for like creating caves, because back in, when we only had ASCII art, caves were like a really easy thing to make. So everybody had caves in their game, but it isn't used much anymore. So constructive grammars or templates, this is the most popular approach in general. The basic idea here is that you have a sort of generative grammar, you have a template with a series of slots, and you have a set of tokens that can go in each slot, and a set of rules for how the different categories of token can interact. So over here, we see examples from Spelunky. We have several different kinds of little level chunks, and we have rules about how they can be put together, right? So like a landing has to be below a drop, for example, things like that. But then you have lots of individual hand-authored pieces from each of those categories that you can randomly pick from, randomly put together in order to create something new, right? We can also see a pretty clear example of this. This is really early No Man's Sky. Everything looks better than this now. But I really like this example because it's such an obvious example of the template, right? We can see here, we clearly have a head slot, a body slot, 4 limb slots, and a tail slots. Now, do any of those go together in terms of this creature looking good? No, they were missing a whole bunch of rules in terms of saying what actually is going to look good with each other. But you can really clearly see the slots at play, which I really like for this. So the downside of constructive grammars, despite them being so popular, is that there's no guarantee if you're using them for levels, for example, that they'll lead to completable levels. Or for like, creatures, there's no guarantee it will lead to a good-looking creature, right? The sort of combinatorics of this makes it functionally impossible to test for all possible output, right? So you often wait until a game launches, and then you figure out, oh no, there was a possible combination of here that breaks everything if it happens to happen, right? So here, for an example, is one from Remnant from the Ashes, which is like this 3D run and gunner, sort of like a Souls-like with guns, right? And in this case, you have inaccessible reasons just because of how the map was procedurally generated. This was eventually fixed. They patched this out, but it took until they launched to figure it out because of how many times they'd have to run the generator to find that. And it can take a lot of hand authoring of tokens to ensure that you have like good level variety. The alternative here would be something like noise. So noise is super duper handy. Noise was originally developed for texture synthesis. In fact, it was first deployed for the first Tron movie for like the backgrounds and things like that, which is pretty fun. If you've ever listened to white noise, you know what noise is. Noise is basically we've taken randomness, random values on a grid or some sort of sequence, and you've added some rules to give them the appearance of structure. This really clever academic in our area, Kate Compton, who's now the director of play for Lego, which is such a cool title. She refers to this as flavors of noise, and she's American, so she doesn't put the U in it. You can see two here examples. So we have Perlin noise. This is really, really popular for landscape generation. And then we also have value noise, right? Which is not really used for landscape generation, but you could imagine using it for like, I don't know, like a weird face mask or something like that if you wanted to generate one of those in the games. Yeah. Yep. No. It's a good point. No, it's really cool stuff. So Perlin, it's like we're in sync. This is a favorite for PCG landscapes. So if you, for example, played Minecraft or Skyrim, you have been on a Perlin noise structure before. So Minecraft uses actually several layers of Perlin noise to generate its structures. And we have Skyrim here. Skyrim obviously isn't procedurally generated. If you haven't played Skyrim, maybe you don't know, but it's not procedurally generated. It's fixed every single time you play it, right? But basically what they did for the initial landmass generation was they kept on just rolling PCG Perlin noise landscape generation until they got something they kind of liked. And then they just sort of went forward from there, right? So this is like online, which means that the PCG is happening live in a game, versus offline PCG. Right? It's happening during development, but the player doesn't get to see it. Make sense? Okay. Next, we're going to go over an example in Unity of generating Minecraft levels. I'm going to do this from almost scratch, and I'll show you how fast you can do it. It's not quite scratch. I wrote 2 scripts ahead of time. But they're really simple scripts. I'll show you them. Wait for that to load. Give that a second. This is 2019, so it's slightly earlier. We're no longer in light mode. Thank goodness. I was so scared while we were in light mode. So let's take a look at what this just does if I just run this. And we can see that it creates a big, flat, white rectangle, or square in this case, right? Not a lot is happening there. But if, for example, I were to unmaximize us and take a look at our scene view or our hierarchy, we can see that what's happening here is we have a lot of cubes, so many cubes, right? If we actually take a look at any one of these cubes in particular, we can see that even though this landscape looks like it's just big flat white cubes, there's actually very subtle, oh, you can't even tell because it's glowing so much, it's so bright. Very subtle differences in terms of the Y values. Very, very subtle. Too subtle to even really notice, right? Let's take a look at what scripts are at play here. So we have MapMaker, really simple script. Here's what MapMaker is doing. At start, so just a single time, it's going to run through a 100 by 100 cube, which is centered at 0, 0, right? And it's going to instantiate a cube. So this is what instantiation looks like. We were going to do this if we'd gotten a little bit farther on the Unity thing yesterday, but we didn't get to it. So this is how you create a new thing from like an example. Then it's going to grab a Perlin noise value. So this is fixed. This Perlin noise is basically, imagine it like a massive texture, right? Massive, really dense texture, right? And we're basically grabbing, it's grayscale, obviously. So we're going to grab a value from it, and we're going to add that Perlin noise in terms of the height of the cube, okay? And then we're going to set this cube at this position, and we're going to pick a color. We'll get to the picking a color in a second. So you'll note I've already given myself, like any good chef, I've given myself suggestions about the things we need to do to actually get this to work from here, but it's really minor. So if we have this case where we have these really subtle changes across the Perlin noise, maybe the problem here is that we just need to make the changes bigger. And a simple way to do that, we can just multiply by a constant, right? And then it's going to look like more difference between them. So let's run that. So it's hard to tell, but if we go back and we look once again at the scene view, you might be able to notice, oh, it might be too low res to tell, but there's very slight, you can see the slight steps, right, that are happening there. It's a very slight difference. But the problem is that like the bits that we're looking at of this Perlin noise thing, there's too slow of a change happening. We need the change to go faster. And so for the change to go faster, we're going to instead divide each of these values by 10. And to do that, we now get something that looks like that. Starting to look a bit better, right? We've got sort of hills and valleys. It's like I'm in Kamloops, right? So just with that, if we're only pitting a single variable, we're only picking a single variable value in terms of this, right? Only the height of this, we're not going to really get anything that looks particularly good. What we want is for this Perlin noise value to actually impact multiple different things. And don't worry, I already have the script ready for that because this is a prepared presentation. And what we're going to do right now is we're just grabbing the final index of these 3 indices. If we take a look at our cube prefab, we can go down here. We can see I have 3 values, a sort of bluish, a greenish, and a whitish, right? I'm only grabbing the white right now. But if I were to go back and say, no, 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 instead of doing that, pick the value that we should grab, which color we should pick, based on the Perlin noise. So the higher the Perlin noise, the more likely we're going to pick the last value. The lower the Perlin noise, the more likely we are to pick the lower value. Make sense? And if all we do is that, really, really simple, we can get something that looks like this. Yeah, right? That took like 5 minutes. Now, obviously, I already wrote those 2 scripts, and I obviously know how to work with Perlin noise, but you can get a sense of like how rapidly you could do this kind of thing to get some kind of landscape working for a game, right? So there's also a lot of opportunities here to make changes. So for example, maybe we say something along the lines of, you know what? I didn't really like the sort of the how quickly things were sort of moving there. There's like too many little bumps. Maybe what I want to do is something where like actually instead of 10 over here, I want to use like 5. So it's not as like slow and smooth, but it's not as sort of like choppy and random as that last little bit looked. And if we do that, then we'll get something like, oh, sorry, I went the wrong way. This is even choppier. Even choppier. That's obviously what I was saying that I wanted the whole time. I should have divided by 20. I'm sorry. But you can see here, this is like even more bit crushed as the environment looks, right? But no, we could do instead 20 by 20, which would give us something that's a little bit more smooth. Run that. And there we go. Now that looks like a lot smoother, right? Maybe we want something in between, et cetera, et cetera, et cetera. There's something interesting going on here. I'm just going to run this code over a few times, and I want you to see if you can tell me what's happening. Well, there's repeated structure. That's definitely true. It looks symmetrical, but there's this other thing that's happening. I was saying this is procedural. Do we look like we're getting any differences here? No, my seed's the same. So again, if we think about this as being a massive texture, we can see up here that I have an offset. So that offset is 0. I'm starting in the top left corner, basically, of this big texture. I could pick any other seed value, and I would get something entirely new. So for example, just as a reminder, this is what the 0 offset looks like. Let's take a look if I change this to 10, for example. If I change this to 10, we instead get this. So you can see it moved things over a little bit. Because again, imagine it like a big texture. I can pick a really big number. We could go with like 100, very far away from where we were before. And if I do that, then I would get this. Cool, huh? The fact that there was symmetry is just because there happens to be symmetry at that part of the texture. Don't overthink it. That wasn't about anything having the Perlin noise. It just happened to be worth picking. Now, if ever you have in like Minecraft picked a seed that you're starting with, guess what? This is what you were actually doing. There was this and several other constructed PCG generators in there that have the same kind of dependency on some starting value, right? And so by picking a seed, you're picking where you start. This is really handy for doing things like sharing different worlds with your friends, but it's also really handy in terms of development, right? You could go through and you could say like, oh, actually, I only really kind of like offsets 15, 35, and 100. So those are the only real levels I want to be able to generate with this thing. And now your PC generation is just pick a random number from the set that you've selected that are any good. Make sense? So there's lots of ways that you can use this offset information. Cool? Cool. And as before, I'll give you all these Unity things that I ended up showing you today. Okay. So why do we think constructed PCG is so popular? These sort of templates or grammars, these sort of noise-based approaches, cellular automata. Why do we think they're so popular? What are people's ideas? Yeah, it's pretty easy to implement. I mean, you saw me messing around. I obviously made one mistake, but that took, what, a few seconds to fix, right? It's really fast, so that's nice. So it's really easy to like iterate on in this way. And this kind of iteration where like, oh, I kind of like that. What if I change it like this? Oh, I kind of like that. This is very common in terms of working with PCG. Any other ideas? Why do we think it's useful? Why do we think it's well liked?
You can still carry the narrative, the same feel throughout them all.
So notably, right, constructed PCG could even be used for narrative, right? But it's certainly true that it is sort of PCG generally, not just constructed PCG specifically, but it's sort of nicely modular, right? You could be generating just camo for your enemy units, right? And not generating anything else in the game, right? Any thoughts on constructed PCG specifically? Sure, but that's just PCG, right? So there's also search-based PCG and PCG via machine learning. Determinism, yeah, that's huge, right? So this sort of seed-based thing of being able to share things like that, that's great. Especially if you're using it offline during development. So I'm going to say it like this: controllable, which is part of the determinism, but also in terms of like I just need to go in there as a designer and like muck around with the different pieces to be able to control it and make some changes to what's possible to generate. It's fast. So it tends to be done in one shot, right? So you saw how fast like the Minecraft stuff was. It was just as fast as I could get 100 cubes on screen. But also, like if I was doing the grammar or the template thing, it'd be as fast as many slots as I have to pick, right? If I have 5 slots because I have, a head, a torso, front limbs, back limbs, and a tail, I just do an O of 5 pick and then I'm done, right? It's really, really fast. And it's intuitive. So people, designers who don't know how to program, really like thinking about just like taking a problem and breaking it into pieces, right? This is a really easy way to think through these problems. So with that, I want to ask you a question. How old do you think the newest game AI technique I've mentioned so far in this presentation is? I want years, by the way. So we have one guess of it hasn't been since 1970 that there was a new approach mentioned in here. Any other guesses? 1989. Okay, so that would be, sorry, not even meaning to die here on you. That'd be like 30, 35 years, something like that. Sorry? Something that Newton did, so we think maybe hundreds of years? Okay, so it's not that bad. It's about 10 years. So the dialogue system for Left 4 Dead, which then later used in Hades, right? It's almost literally the same dialogue system for both of those. So it's actually more like, I don't know, 11 or 12 years at this point, because Left 4 Dead is about that old. But that's the oldest one of these. But still, there hasn't been a lot of advances. And you might have, somebody mentioned ChatGPT is the first thing they thought about when it came to AI, right? So you might say, well, now hold on. Why isn't anybody doing anything new with these technologies? Well, let's talk about it. So while we're sort of past talking about these, let's talk about sort of what goes beyond. What is beyond the scope of these things? What's sort of maybe the cutting edge of games, right? So for example, if we're thinking about ChatGPT, there's this game called 1001 Nights. It technically sort of relaunched in like pre-release in like 2023, just in the festival circuit. It hasn't actually launched on Steam yet. I don't know if it actually ever will launch on Steam, but it's listed on Steam. The idea of this game is that you are playing as Scheherazade from the titular 1001 Nights, and you are basically writing a story in free text. You write a story however you want to write a story, and then a chat GPT king. Oh, I forget the name of the king in the Scheherazade story. He's an evil king. Ah, very scary. He is going to respond to your story, sort of evaluating it, and he might mention specific items that are in the story. And when he mentions those items, you can grab those items, and then you can use those items in an RPG battle with the king. Yeah. Sure. Well, the fact that it can actually sort of evaluate your stories, right? Now, is it doing any sort of real evaluation? We can argue, but there's something there. It's also the case, I didn't mention it, but like all the items, visuals are being generated with a diffusion model, so that's a bit new, etc., right? Everything obviously is based on something, but it's fairly new. Okay, but let's talk about the future of games. I put this in quotes. So I do this fun activity where I'm going to give you a quote, and then I want you to tell me what year it's from. Here's the quote. Significantly, developers overall reported that AI was becoming a more important factor in game design than it had been in the past, often being assigned an equal priority with graphics and sound in the initial game design and allocation of resources. This goes on to talk about this. It talks about like some neural networks in some games, things like that. What year do you think this quote is from? 2019. So we have a guess. Aughts. Okay, so like 2000s, late 2000s, something like that. Sure. If we're talking about neural networks, those only really took off in like 2005. So that's a fair guess. In the back, I saw a hand for a second. 2007, specific. We're getting a specific year. Any other thoughts? Okay, no other thoughts? So we've got sort of like the 2000s and maybe the 2010s are sort of the guesses here. And as a reminder, I just told you a second ago that the latest thing that we talked about before we got to this section was 10-ish years ago. So that would have been in the sort of 2010s, right? So let's see where this is from. This is from 1998. Stephen Woodcock's Gamma Sutra, which has now been renamed as Game Developer or something, I forget exactly. Game AI State of the Industry from 1998. And yeah, we had neural networks back in 1998. In fact, we've had neural networks for, depending on how you count, since like the 1960s, 1950s. But anyway, so if we talk about learning in games, learning happened back with Black and White and Black and White 2. Did anybody ever play Black and White or Black and White 2? Yeah, there we go. Really fun, weird games. These were using decision trees. Speaking of, you mentioned decision trees earlier. Or Creatures. So Creatures and its sequel, Creatures 2, this is what Stephen Woodcock was talking about in 1998 in terms of people being like, whoa, look at these cool things you can do. In this game, you had these little creatures that you trained with a little neural network. It was this little neural network running in the game that would learn how to act as you were interacting with it in this sort of weird generation ship Simsy game, right? And after this, people stopped doing this in games. There's a lot of reasons for that in terms of it being sort of difficult to control, difficult to like have a crafted player experience, difficult to design experiences around these things. But let's, talk about some of these technologies anyway. So if I'm talking about, generative AI and deep neural networks, right? What this means is that these are models with a whole bunch of neurons. These are not actually what the neurons in these models look like. This is an image of like a neuron illustration from the kind of neuron that's in your brain, right? Has anybody seen an illustration like this before? Maybe in a biology class? Okay, so the majority of you. The way this works in your own brain is you've got like millions of these suckers, and they basically pass electronic signals along between different parts of your brain in order to like have you understand the words I'm saying to you, for example, or move your body at all, and so on and so on and so forth, right? So basically in the 1940s, maybe depending on how you ask, even earlier than that, in like the 1800s, people sort of knew about these things. They're like, what if we made a mathematical model of one of those? And so they came up with this, which is referred to as an artificial neuron, right? It's really simple. And here a bigger version. All we're going to have is some number of inputs, those are our x's, some number of weights on those inputs, those are our w's. Inside of our neuron, we'll have an activation function, which just tells us how are we going to combine our weights and our inputs. In this case, I'm just basically doing a linear activation, which just means I'm doing x times w. That's it. And then I'm giving you some output or outputs. And that's it. That's a neuron. So let's say that I had a text processing example. So this would be something like, this guy, Matthew Guzdial, was doing a talk. He gave a text processing example. If I did that and I trained a single neuron on this, we would have it predict the words in this way. So if given this, the neuron would predict Guy. If given Guy, we would predict Matthew. If given et cetera, et cetera, et cetera. Make sense? And now I'm saying we're predicting words. The neuron would not actually be predicting words because they have to use math. So we would just use like a vector representation for our words, something like that. Don't worry about it too much. But even a single neuron could learn an example like this. But what happens that's interesting is when you take a single neuron and you put it with other neuron buddies and you create a neural network, right? These are like the graphs that we showed earlier. These are directed acyclic graphs that can pass more complicated information along. The simplest neural network would look like this. It would have 3 layers. You would have an input layer, which is where the inputs come in. That's why it's called that. You'd have an output layer, which is where the outputs come from. That's why it's called that. And you have a hidden layer, which isn't the input or the output. People act as though the hidden layer is some sort of like mystical, mysterious land when they talk about teaching neural networks. It literally just means it's not the input or the output. That's it. It's still just each one of these neurons is one of those things from earlier where it's taking some inputs, doing some math, and getting output. Sure, transitional is nicer. It's a little bit less mystical. Anyway, so they date back to the 1940s or maybe even the 1890s, depending on who you ask. There's a big promise during the last AI summer. We're currently in an AI summer, which basically means people care about AI. There's funding for AI. Businesses are trying to do things with AI. This is not the first time that's happened. It's the 3rd time it's happened. In between every AI summer, there's an AI winter. It's basically like Edmonton, where I'm from. So it's like just winter or summer. Those are the only seasons. There's basically no real success until the big data revolution. So this is the guesses around the 2000s. Those are good guesses because it was until like 2005 that people actually cared about this approach at all, because that's when we had enough data to actually train these things for the first time. Like, why? Well, you had more data and you had some specialized architectures. And because of the specialized architectures and computation power, you could also make them bigger, right? So before transformers, which is, if you know Chat GPT, GPT stands for a generative pre-trained transformer. It's just a transformer. We're going to get to how a transformer works in just a second. But prior to transformers, LSTMs were the state of the art if you're talking about sort of how do you process text or anything. And the way that it worked is they could hold a particular index from your sequence in memory. So they could basically, quote unquote, remember something to later process something else. So let me give you an example because that's the easiest way to do it. Let's go back to that same example from earlier. So same text. This guy, Matthew Guzda, was doing a talk. He gave a text processing example. If this was an LSTM, we would get this. This LSTM cell would give us guy, and we would hold nothing in memory, right? So there's nothing in memory right now. Then we could say like Guy and Matthew, and then later on, we could hold Matthew. As soon as we processed Matthew in our memory, we could hold it in our memory, such that later when I'm having to predict a pronoun, I could remember Matthew. And I could say, oh, most Matthews are he, hims. Let me predict he. Does that make sense? So this is allowing you to sort of look further away when you're making decisions, sort of long-term decision making. Cool? You can actually use LCMs for Mario Brothers. This is just a fun example. So this is my buddy Adam Somerville who applied this for generating Super Mario Brothers levels. And you can get some pretty decent stuff out of them. Anyway, that's an aside. So large language models are just big transformers. I hate the phrase large language model because it doesn't mean anything. It's just a big transformer. Anyway, transformers work like this. They originally set up to do translation tasks. So je suis étudiant, it goes in the transformer, we get I am a student out of it, right? So it's translating from French to English in this case. So they're originally set up just for translation. But then some wise guy was like, hey, now hold on. Going from one line of text to the next line of text is kind of like translating from one language to another, isn't it? And they applied it to that, and by golly, it was pretty good. The way that it works is it has what's called a self-attention layer. So previously, when we were looking at like LSTMs or a single neuron, we had to only get one thing at a time, right? We were only seeing like the previous word, and maybe we could remember some earlier word, like for LSTM, but we didn't actually get to like see everything that we were supposed to be getting as input. But that's not true here. So we get to get everything as input. We get the whole phrase, je suis étudiant. And the self-attention layer says, as I'm trying to process a particular word, which of these words from the input do I pay attention to? So when I'm making a prediction about like I or am or student, which of these words from the input matters in terms of that prediction? Does that make sense? Cool. So that earlier example, this guy Matthew was doing a talk. He gave a text processing example. We would get in the entirety of this line. We would get back the entirety of the next line. And this is how ChatGPT works, and like every other large language model works. The context gets bigger. That sort of input that it can get gets bigger as these models get bigger, and the outputs that it can make get bigger. But then you basically take this and you train on the entirety of the internet. Plus, you do this thing called RLHF, where if you're wondering why they're like weirdly polite, it's because of this thing called RLHF, where they basically have this extra little reward thing for being sort of like polite or trustworthy sounding, and that's why they sound the way they do. So even with all of that, you know, we can get something like AI Dungeon 2 as an example. Right? Did anybody play around with AI Dungeon or AI Dungeon 2? Okay, one person, two people. So I'm just going to read you out this. This is an example of somebody interacting with this large language model. This was basically GPT-2 at the time. And the things with the sort of greater than symbol, that's output from the model. So we the human, or sorry, those are output from the user. So the AI says, I need some help. The human says, with what? The AI says, with getting my computer working. The human says, did you try turning it on? The AI says, no, I tried using the mouse. Human says, press the on button. The wizard turns around and stares at you. What the bleep are you trying to turn on? He asks. Turn on the computer. How the bleep would I know if you turn on the computer? I turn on the computer. So you're telling me you didn't even know what was going on when you pressed the on button? It's on now. That's not true. I turned on the computer. Then fine, now download Manjaro. And so on and so on and so forth, right? So, you know, GPT-2 was a while ago, and you could say like, oh no, GPT-3 and 4 and 5 and so on, they've fixed this problem, haven't they? No, because there's no actual internal representation of the world, right? And you can see this happening here. A wizard shows up. The reason why a wizard shows up because they fine-tuned GPT-2 on a whole bunch of like interactive narrative stories, and there's a lot of wizards in those, and so wizards show up, right? But then, sorry. Totally. So then it also can't tell like the state of the computer because there's no understanding of that, right? It's not acting like the rules from before or anything like that where we're checking particular variables. No variables exist. It's just text, right? And so because of that, it can't really hold on to these things. And it's because of that that despite all the excitement around generative agents and like having agents in games you can really talk to, we're probably not going to see this actually in a game anytime soon, at least not by anybody serious, because it's just not going to give you very good results. Anyway, we do have things like 1001 Nights. There's some demos of that you can see, but not currently available. You have things like this. You have things like Liz Fiacco's sort of lab assistant setup and things like that. But at this point, I've reached the end of my prepared material. So I'm going to open the floor to questions, and I have a whole bunch of other sort of slides as well here that I could show you depending on your sort of interests. But I'm hoping now that we've done sort of an overview of everything AI in the games industry, you might have particular questions about how you do particular things. Cool? Any thoughts? Yeah. Mhm. Sure. I was not intending to talk about my own stuff, but I can talk about my own stuff. Let's see. What's the easiest way to do that? Let's see here. Uh, yeah, I mean it's a good question. My thought is just I have so many hecking students that it's hard to like narrow down. So like, this is a presentation. I'm not going to do this whole presentation, but a lot of the research that I work on is about like how can we expand who is possible, who can possibly be a game developer, who can make games, to not just sort of programmer types like us. But I talk about like the problems with these things, why PCG doesn't solve it. We talk about like ways that you can solve representations, right? Representations are a huge problem, actually. If we think about sort of how do you represent a level in such a way that something like Doom and Mario can both be recognized as the same kind of thing by a computer, right? That's kind of tricky and fun. And so we did that with this thing called tile embeddings, which means we can now generate game levels for games that we've never seen before, which is pretty cool. We have some cool novel low data PCG stuff. So like very low data PCGML, generating stuff with machine learning stuff. This is tree-based reconstructive partitioning, for example. Maybe we'll have a roguelike celebration talk on it this year. Roguelike celebration is worth checking out, by the way. We also done some cool stuff with like mechanics, right? So like learning mechanics from video. So here's an example. Let me get down to it. These are examples of learned game mechanics. So these are like fake game engines running on the left for Super Mario Brothers and Mega Man. That are running purely from watching gameplay video, and then we have an actual, withheld test video on the right. And this is like the closest approximation we can get out of it from our like fakey fake engine. And it's not perfect, but we literally learned this from like 2 gameplay videos, right? And we learned a lot of the same mechanics, and these are actually represented as like computer code learned mechanics. So we can like dig in there and mess around with them. And then we took that concept and we took it to this thing that we're calling Mechanic Maker, which is basically this way of, rather than grabbing this from like gameplay video, what we're doing is we're actually looking at, well, can we just have a human being give us examples, like fake gameplay video for a game that doesn't exist? And then can the system learn actual code that will like define the example rules that you're demonstrating, right? So in this video, for example, we have this little like shooter. This lady's moving up and down. If you hit the arrows, currently it doesn't learn anything, so it doesn't know better. And you can have it learn that when you hit the up arrow, then this lady should move upwards. So you can see there, it's with this example so far, and then it's predicting nothing happens because it hasn't learned anything. That's actually correct in this case. Nothing should happen if the button wasn't pressed. But here we go. Here's another example. Go to the next frame. I hit the up arrow, and you could see there, I don't know if you noticed it, but it actually predicted the character should move up because we learned if that button is pressed, the character should move up by a position, right? And that was just from the example. No code had to be written for that, right? And in fact, it has no knowledge to begin with. There's no templates. There's no example rules. It has nothing to begin with, and it learns that. If I jump ahead in the video a little bit, you can see that I give examples of going up and down, and now I'm playing in real time. So I'm having this character move up and down in real time just based on that learned code. Now, this is like 2 if statements. That's not all that interesting. But if we keep on moving, I end up sort of giving examples of like shooting fireballs, like Kamehameha blasts out of her hand. And if we then go into the sort of play view, you can see here that's from what, like 29 examples. We can sort of go up and down. We can still do that stuff. And then we can, shoot a whole bunch of Kamehameha blasts out of our hands, right? And that took, 30 frames to be able to get that behavior. And it's obviously, not the best thing, the coolest thing in the world. But if you don't know how to do any programming, it's pretty neat to be able to say, like, here's just some examples, then you can do this thing, right? And then, we're also doing some stuff around generating mechanics. So this is this environment we stole from Mike Cook, who's a famous guy in our field. He did this work called Mechanic Miner. We meant to call this Mechanic Miner 2, but my student has dyslexia, and he accidentally called it Mechanic Maker 2. Oops. Anyway, but we basically ended up with a situation where we can like generate new mechanics that allow an agent, this little guy, to solve this environment when it's normally not solvable, right? So there's no actual way. The jump height you can do is not sufficient to go over this by default. So then if I grab this one, we can see some of the example like rules that we get is generated here. So here's one. It sort of invented a super jump. That's kind of boring. But here's one where it invented a teleport, or like a Y teleport. You just teleport a certain amount up in the Y axis, which allows you to like clip onto this sort of like T view here, which is pretty cool. And here's one where it just moved fast enough to be able to clip through the wall. And so, all these different ways that it can sort of get over there. And we're using reinforcement learning, which is like very common in the like automated game playing sort of space, or robotics and things like that, to like have the agent trying out these different generated mechanics and figuring out which one of them works. And then we do lots of stuff on the side. We do some cool stuff with like music. So this is some work by my student Anahita, who just recently graduated, on trying to get these giant music models, so like Music VAE by like Google, and get them to actually generate Iranian folk music, because they're only trained on like jazz and pop and rock. And Iranian folk music, if you've heard it before, sounds very different from those, and it can't do it by default. But with some little cool transfer learning tricks, you can get that to work. Whereas my student Dagmar, they're working with like creating animation tools for artists, right? So working with artists, sort of human in the loop style, where a human artist gives the top row of these, and then the system responds with the bottom row. These are test examples from real human artists who like really just gave us these little bits of animation that they wanted, and we sort of automatically color them in. You can see on the top row, worked really nice. We've got a little fox that's dancing around, right? And the bottom row doesn't work very well because it turned out that like none of our training data had jumps in it. And so it was like, had no idea what to do with that. But yeah, working in those sorts of spaces. And as I mentioned, I have a ton of students. There's all my students except for Seth Cooper, who was visiting at the time. He's not a student, he's a colleague of Joseph's and I's at Northeastern University. But I have a ton of students working in the space. This is only like a selection of like 4 students' works. But you can get a sense of like the kinds of things that I do. Yeah, thank you. I appreciate the prompt. Happen to have this presentation combining some of the work in some thematic way that I can reference. Any other questions? Feel free to ask me questions about like, oh, I like this game. How does that work? How does this AI work? Or if you were to implement something like X, how would you do it? Or I don't know, whatever you're curious about. Yeah, please.
right?
Totally.
With those specific flaw points that you have, that's the main whole plan, right?
Yep.
Those AI, so they always know what to do to use billing.
Yep.
So would those just be conditions that they follow?
Yeah, so the Souls people only use finite state machines. That's literally all they ever use. And it's because, right, what did I say about finite state machines? They're really good in terms of like working with designers, right? So the clever bit about there is not that like the AI is making clever decisions, it's that the designer was really good at figuring out how do you make this really fine-tuned boss experience. And you can see that they're finite state machines. If you know to look, it's really obvious that they're finite state machines because you can see each of the distinct states that they're transitioning between, right? And there's no like default that they're starting with. There's no like default behavior that they're doing. It's like a set rhythm of states that they move throughout the fight. Yeah. No, totally. Yep. 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 Totally. No, totally. And again, like the easy thing would be to make a enemy that's just impossible to defeat, right? The really clever thing is that you can see the patterns. The patterns are set up to be really obvious, and that you can then read them and you feel awesome once you figure them out, right? Like maybe each one of its attacks kill you, but before it does its attack state, it has a massive wind up state where it will go like only if you then don't move and you get hit by it or you don't dodge at the right time do you actually get hit by the thing. But it's really obvious what it's going to do and what attack is about to actually happen once you know to look for it. Sure, yeah. Very much similar. Good question. So they're not actually predictive. Sure, sure. So, game AI cheats all the time, right? Cheats all the time. Because, like, if we think about, if you're playing a horror game, like if Mr. X is chasing you in Resident Evil, Mr. X knows exactly where you are because the game knows where you are because you're a virtual entity. Like, of course, but he pretends that he doesn't know where you are because the rules say that if you hide in this cabinet for 30 seconds, that he forgets that you ever existed, right? So it's a similar thing happening with Souls likes. It's just using a finite state machine. There's no predictions. It's not predicting what you're going to do, but it has all this information, right? It knows exactly where you are. It knows exactly how much mana or whatever you have, whatever the equivalent is. It knows what your health is at. It knows how far away you are from it. It knows what buttons you're pressing, right? It doesn't need to do anything clever in terms of predicting the future. It can just have all this information and then say like, well, this is the best thing that I can do, not in terms of beating you, because again, that would be so easy, but in terms of giving you this sort of interesting, predictive, pattern matching experience. Does it make sense? Is there any questions online? No. Any other questions? Good questions. No? None questions? I'll be here till 4:30. That's when my taxi's coming. You had a question? Sure. Sure. Yeah, yeah, yeah. Hades has a lot of replayability. Sure. I've seen Red Dead Redemption. Sure, sure. So Red Dead Redemption 1 and 2 do have a number of interesting AI things, but it's not in terms of the story at all. So right, it's not in terms of the story at all. So, or the character interactions. So again, if we go back all the way, I don't know if you remember this because this is quite a while ago. We're going to talk about AI as making decisions that a human would otherwise have to make. So there's actually no decisions being made in the game in terms of the characters, right? These are all hand authored by a person. They're saying of, oh, if the character went this route, then play this cutscene, have this dialogue cue, do this, do this, do this. There's actually no decisions being made locally by the AI about what to do in these different scenarios. So that's not to diminish that, right? It's super cool, right? And the characters feel super alive, but that's about the quality of the game's writers, right? Of just like, oh, let's imagine ahead of time about what kind of state the player is going to be in and what information do I need to communicate to them with this character? And oh, what's this character's voice sound like? So how would they say this line, right? So that's about the quality of the game's writers. That's getting you into things like interactive storytelling and things like that, right? You can look up like Emily Short is like the goddess of interactive storytelling. She is if there's a writer in video games, they're basically take her word as law. She has a great blog, which goes over a lot of this concepts around how do you do this kind of writing, right? The interesting things about Red Dead Redemption 1 and Redemption 2, for example, for Red Dead Redemption 2, the landmass is actually procedurally generated. So it's similar to Skyrim. But what they did was this very clever thing is they took the actual like parts of America because I don't know if you know about this, but like America, there's lots of satellite images up there. And so they could basically take the satellite images and turn that into 3D geometry. It's the same kind of thing that like Microsoft Flight Sim. Did anybody play the most recent Microsoft Flight Sim? Some people are nodding. They did that, but for the whole world, right? So they just did it with like a little chunk of America, and then they like filled it in with procedurally generated like tree placement and NPC placement and things like that. And then humans went through and like did all the editing passes and polishing passes and adding the quests and adding dialogue and so on and so on and so forth. And there's also some really clever things they do with the way that they change out animations. So they have like a set human body type and they have set animations on that, but the animations are actually dependent on the landscape around them. So for example, if you're like, or the context around them. So like if a character is carrying something heavy, the animations are procedural such that like you'll actually like be pulled down by the heavy thing a little bit. Or if you're going up a hill, you'll actually like slant a little bit as you're going up the hill. So there's all these clever little bits that they added in there to like really bring life to what was happening in terms of the AI. Does it make sense? They're not fully procedural. So basically, a human had to go through, they animated the base rig, right? With like a carrying animation, for example, right? But then the animation itself is parameterized, by which I mean, depending on certain elements in the world, the animation will play differently. Does that make sense? Any other questions? Good questions. So just to say, because I don't know if anybody asked questions, but in terms of the data science stuff, there's a really good video that's online of a recording from Alex Zook from the Knowledge and Extraction Games Workshop, KEG Workshop from 2018, where he talks about being a data scientist at Blizzard at the time, before all that nonsense that happened with Blizzard in the past, few years. But they talks about things like how do you figure out what the player types are? How do you do better matchmaking, right? How do you figure out for designers, what parts of the game are working well and not working well, right? So that's this sort of additional layer of AI in games. Nothing the player sees, right? This is all in the back end, all in the development end, but it's a whole other area that I could easily do, 4 or 5 lectures purely on that, and I already did a very squeezed down version of this. Worth saying. All right, last call. Any remaining questions, including in the chat? Happy to look at this. I think there's a delay though on that side. Even smaller companies care about this, right? Because if you start having, even hundreds of people playing your game, right? If you have 10 people playing your game, then you've done a play test. You can look through everybody's responses, right? If you have 100 people playing your game, you're at a point where like you can't possibly go through everything yourself individually. There wouldn't be the time for it, right? So you start doing things like clustering. Has anybody done clustering in like an AI or machine learning class before? Okay, somebody a little bit. So clustering is about like how do we find out the sort of groups, hidden groups? How do we group things together in sort of the most optimal way possible at a high level, right? Yeah. So that was that example specifically, and specifically thinking about what are the kinds of different decks that exist, right? So anytime that we're trying to find out what kinds of players you have, we might do that, right? Because we just can't possibly go through everything. But it's also really simple things like if I have a map, right? I can track on my map. If it's an online game, I know exactly everything that happened, right? I know where every player death occurred. I know where every, pickup occurred. I know where every item occurred, et cetera, et cetera, et cetera. And I can start looking at my map to see, are there weird hotspots? Like if this is a competitive game, is everybody dying in like very specific parts of the map? And is it because there's maybe a balance issue, right? This would be something that isn't possible unless you're starting to do data science stuff and we're like aggregating all these results together in some way to make it actually processable to a human designer who actually has to go back and make decisions. So there's a lot of like, how do you deliver design insights? How do you give feedback to the game's developers when you have hundreds or thousands or millions of people playing your game? Does that make sense? Exactly. Or like characters, right? In Valorant. Wow, it turns out that like this matchup is really in one direction, right? Exactly. And that doesn't mean that like the designers are only making decisions based on like pure objective data, right? There's a lot of gut here, but there's also a lot of like, if we're talking about being a designer and balancing games, there's a lot of just having to placate your audience. If the audience believes a character is overpowered, even if the character isn't actually overpowered according to the numbers, you still have to make a change there, or else they won't stop complaining about it, right? Any other questions? Okay. Well, if there's no other questions, I think we have about an hour-ish break before we will start again with some cool stuff on microtransactions and things like that. I'm hanging around here. I'll be here till 4:30. So if you want to come up and ask me any questions or talking about any of these things, I'm more than happy to chat about these things. And otherwise, thanks for being a good audience.
Thanks again.
Yeah, happy to. Totally. Oh, wait, was there questions? I'm gonna need to rewatch and see the stuff about Pac-Man more. Subnautica used some really cool analytics.